Welcome to this recording of high tunnel ventilation put together by Mike Merritt from Rimmel Greenhouses, Kathy Demchek from Penn State University, and AJ Both from Rutgers University. This is part of a larger project called TunnelBerries, which is funded by the SCRI.
High tunnels. High tunnels are designed for natural ventilation, which usually involves the rising of hot air up to a peak with an intake supply somewhere on the structure, and then the air escaping via an opening. Since we're going to focus on high tunnels today, I'm only going to go over the different configurations you have that are non-mechanical, i.e. electrical. So we won't be talking about exhaust fans or evaporative coolers or anything like that. The first thing that we try to do when we are talking to a customer about the ventilation options is we need to ask what it is you're trying to accomplish in regards to temperature and airflow. And that is obviously a function of what you're going to grow. So some plants require consistent temperature. Some can take variable temperatures and humidity and airflow, etc. So you just need to know what it is you're trying to do. Once you know that, then you can design the structure around your plant. So you need to design in sufficient vent openings to ensure that you get the desired temperature and airflow. These openings can be on the ends of the structure, it can be on the sides of the structure, it can be on the roof of the structure. And I'm going to show you various examples of that at the end of the presentation. We have lots of pictures. For the ends, you can have doors. So you can open up doors to cool the structure. You can put shutters in your end walls or louvers. On the sides, you can have roll-up sides. There are also roll-down sides, and there are side wall vents that you can use. On the roof, you can use ridge vent systems, which open at the peak, or you can place louvers high up in the gable to allow the air to escape through the peak. Question: are taller tunnels better? The answer is yes, because that will give you more area within the structure to allow for general air movement. Now you have two options when you're looking at the different systems that can operate these openings. You can either be manual or you can go motorized. Obviously, it's a function of what the plant wants. So if the plant can take lots of different variable temperatures and airflow, then maybe you don't need a precise way to maintain those set points. So you might want to make it manual, which means you have to go do it yourself. And that is a function of your time commitment, i.e., are you a part-time farmer or a full-time farmer? Are you going to be around to operate that opening? And it's a function of money. Obviously, automated systems, motorized systems, they require more money. Right now, for us, most of the ventilation systems used are still manual, but we are seeing an increase from farmers that have participated in the NRCS high tunnel program, because we're finding that these new growers, they have a day job and they need to automate their ventilation systems in order to take care of the plants when they're not around. Freestanding tunnels. Orient perpendicular to your prevailing wind direction. The predominant air intake on a high tunnel is from the sides. So you want to be perpendicular to the wind direction in order to get the full advantage of the airflow into the tunnel from the sides. There are some people that will orient their structures such as the prevailing wind is coming from the north, where they open up the doors and just let the breeze carry the heat right out. Topography is another thing to look at, where you can put a structure up on a grade, and because hot air rises, Mother Nature will take care of it and cool a tunnel. Pretty good picture of that a little bit later. Gutter connected. I guess the only gutter connected high tunnel that I know of would be the hay grove structures, where they seem to be open pretty much on all sides and can be closed on all sides as well. If you are looking at any other structure besides a hay grove, say a standard gutter connect that uses large gauge square steel or round steel, it will be almost exclusively cooled by some type of a motorized system because of the size of it. And you have an investment that you need to take care of with a structure that size. So you want to ensure that the plants that are inside it are being taken care of. So you'll find large cooling systems on a gutter connect, whether they be at the ridge or large louvers on the end walls, etc. There's also sidewall vents that can be used on those as well. There's a neat picture of the topography example. I kind of wonder what happens when you get a big gust of wind, though. Does it take off like a parachute? AJ, your turn.
Okay, if you look at the different physical principles that are involved in ventilating a tunnel, then there's two things we have to look at. The first one is thermal buoyancy, or the stack effect, or the chimney effect, which you're familiar with from your fireplace. When you light the fire, you heat the air above the fire, and that fire then rises because it's less dense. It's warmer, it's less dense. It rises in the chimney and escapes out the top of the chimney. We call that thermal buoyancy. And the other effect is the wind effect, which means that as air moves around the structure, and when you take accurate readings of the wind conditions around any structure, you'll notice that there's almost always a little bit of wind. There's very few hours in the year when it's completely wind still. And that air movement creates slight pressure differences on the leeward and then the windward side of the structure. On the windward side, you have a little excess pressure because the air is bumping against the building. It creates a little bit higher pressure. And on the leeward side, the air is sucked away from the structure, so you get a little bit of a negative pressure. And that pressure difference between the windward side and the leeward side is able to draw air through the structure. Now, the thermal buoyancy, as I said, is really only effective when it's wind still. As soon as there's a little bit of wind, and as I mentioned, there's always some kind of wind, some amount of wind, the wind effect will take over. So with wind speeds of a few feet per second, you will see that the wind effect is the dominant effect. So we have to rely mostly on any wind, outside wind conditions to help us with the ventilation of a structure. We haven't talked about moisture yet, but in addition to temperature, moisture is also very critical. As you know, when you close up the tunnel and you have a full canopy in there, the plants will transpire a lot of water taken up from the roots and transpiring it through the stomates, and so you will get moisture inside the tunnel. And moisture could be a problem for disease issues. It could also accumulate on cold surfaces and then drip on the crop. So moisture is also something we have to worry about. So it's not just temperature, we also have to worry about how we can get rid of excess moisture in the structure. Warm air can hold more moisture, so if you close it up and you keep it, and it warms up and you keep it closed, you will see that air can contain more moisture. But again, when that air interacts with cold surfaces, for example, the plastic, you can see condensation occurring, and that can create a problem. So here's where the non-drip or the non-condensate plastic can be of help. It's not that it prevents condensation, it just makes the water droplets, the beads, roll off more quickly. And so it doesn't create a whole set of droplets on the inside of the plastic, which could eventually rain onto the crop, which could create damage. But it also reduces light penetration. Those water beads on the inside can reflect light back to the outside and reduce the amount of light that you end up on your crop. Obviously, we are concerned about heat retention, and that has to do with ventilation to a certain extent, because as we are trying to ventilate, we want to be careful that we don't ventilate out any heat that we want to keep inside the structure for when it gets colder at night or during a cold day. So we can use some tricks. We use curtains, just like we do in greenhouses, or extra row covers that we put over the crop to keep the extra air layer around the canopy for insulation purposes, to make sure that we can keep the temperature a little bit higher. And as you probably know, some people use a backup heater to try to help with that heat retention as well. I want to talk a little bit about air infiltration. Tunnels are difficult to really make airtight, because it's hard to have large opening areas that we use for ventilation, and then as we close them very tight. So we will have air infiltration, so you will have air movement that can influence the temperature control you're trying to accomplish, as well as the moisture control. And as we already said, we can use the wind direction to our best advantage to improve ventilation. So when you design and build a tunnel, you want to try to make sure that you make maximum use of the wind direction at your site. So this is a picture showing you some very general design strategies that we can follow, and Mike's going to show you a little bit more in detail some of the actual implementations of this. In the upper left-hand corner, you see the typical roll-up system. So air comes in near the ground, near where the plants are sitting, and you see by the colored arrows that colder air, when you ventilate, comes in and hits the plants and then warms up and rises, and you see a hot pocket of air accumulating in the ridge. You can also do a roll down system, which is the picture on the upper right hand side. So now we are opening the sides higher up near the hip board and rolling them down. The colder air comes in at a higher elevation, more off the ground, and so as it warms up, or as it falls down because it's colder, it warms up from the air inside the tunnel, and you can see that the plants that are in the tunnel hopefully will not get hit by the coldest air, and that air will warm up before it actually reaches the plant. If we do that, we may not end up with a very hot peak, but we may end up with a warm peak, because the distance between the opening and the peak is not as large as it is with the roll-up sides in the first picture. We can also add a ridge vent, as you see in the third picture there. We have roll-up sides plus a ridge vent, so the warm air rises and can escape through that ridge vent. And now you see that the peak area has cooler or cold air, as opposed to the other pictures where you see hot or warm air. And then finally, on the lower right-hand side, we have a situation with roll-up sides and large end doors that can open up. And so you see the cold air coming in on the sides. It warms up, it rises, and then escapes to the top of the doors in the end walls. For the natural ventilation and the thermal buoyancy effect, so only really on wind still days and situations, the distance between the opening and the vertical distance between the opening and maybe an outlet. So if you look at the third picture where we have an outlet in the ridge, that vertical distance is really determining the rate of ventilation. But as I said, most days will have some wind, so the wind effect will be the dominant force, and then the pressure differences that wind create will push the air through the structure. That's you, Mike.
All right. Thank you, AJ. At Penn State, we took 5 structures, and we wanted to try 5 different ventilation configurations, and I think we pretty much achieved it. We took a traditional roll-up system, which is manually operated from the side vents that start to open just above the baseboard. Then they're fully open 5 or 6 feet up to a hip board. So we have one structure like that. And then we have 2 structures that have a traditional roll-up system that is motorized, thermostatically controlled, and solar powered. That was provided by us in Advancing Alternatives. The sides, again, they start to open above the baseboard, then they're fully open 5 or 6 feet high up to a hip board. We also installed a ridge vent system. That's our standard ridge vent. It's approximately 3 feet of an opening. We configured it upon a ledgewood structure, but it had the same grade and Gothic characteristics of our structures, the peak that we wanted. And we also installed a roll-up roof system, which is a relatively new product by Advancing Alternatives and ourselves. It's also motorized, also controlled, and solar powered. And these start to open just above the hip board, and then they travel up to the peak approximately 7 or 8 feet, and then they stop. Lastly, we weren't able to find and install a roll down curtain. However, Matt and Kathy, probably working with AJ, put a knee wall on a couple of the structures, which is about 2 feet that goes from the ground up the side, and it pretty much acts the same as a roll down system would. Then our 5 test configurations that we're going to move forward with this spring, where one structure will be manual on 2 sides. Another structure will have motorized roll-up sides from the ground with a ridge vent. Another structure will have the same motorized roll-up sides with a motorized roll-up roof. And then another structure will have the motorized roll-up sides with the, what I call the knee wall on both sides, with a motorized ridge vent. And then the last structure will have the same sidewall with a motorized roll-up roof system. That is Matt, and you know Kathy. This is the structure that has the ridge vent and the roll-up sides, motorized, that start just above the baseboard. This structure is the roll-up roof and the roll-up curtain on the side that has that small wall that's a couple, 2 or 3 feet high. And you can see how it begins to open at that point right up to the hip board. As I said, they're both solar, they're all solar powered. We're able to power 2 structures with 1 panel in 1 system. This is one of our structures. It's a pretty good size one. Looks to be about 30 feet wide. And you can see it has an assortment of cooling options. Obviously the big doors on the end, but they have the roll-up sides. And if you look, they do theirs manually. There's a gearbox on that curtain. You can see the little square, and it has a hand brace that seems to be sitting there. The hand brace will operate the gear. They also have pretty good sized louver up in the gable, which will allow air to escape out the peak that way. We have a wide assortment of different configurations here. The top left is again a different, looks like a type of a knee wall. I'm not sure what it is they're doing on the roof, whether it's a roll-up roof type of system. The upper right has the roll-up sides, and it has a version of a ridge vent that I think Polytex sells those. Lower left corner, let's say a roof type of a system, and then on the bottom right, very large door proponent with a very large louver in the gable. This is a Haygrove gutter connect, where they have to manually roll up the sides, and the end walls are open and can be closed on all sides as well.
Thank you for watching this video on high tunnel ventilation. For more information on berry production in both high and low tunnels, visit the TunnelBerries website or follow us on Facebook and Twitter.